So officially, greetings and welcome to all attendees of the latest AMS Weather Band webinar, Breaking News Event Idalia, with Stephanie Zick and moderator Marissa Furger. This is the third episode, of AMS Weather Band's live webinar series featuring up-to-the-minute weather events. Our focus is to go beyond standard updates to take a closer look at the underlying science, uncertainties, and factors that influence these events, in an effort to provide you with an insider's perspective on the complexities shaping these major weather occurrences. Before we begin, I would like to address some of the guidelines for our webinar today. Audience, if you have any questions during the webinar, please use the Q&A feature on the bottom of your screen, as questions submitted through the chat function will not be considered. We have also set aside some time for audience questions at the end of the presentation, but some questions may be addressed during the course of the presentation if it fits the flow. Now I would like to introduce today's moderator. Thank you, Marissa. Folks, Marissa Furger has worked with the Weather Communications Group at Penn State University for 2 decades, where she produces and forecasts for the show Weather World and teaches courses in weather communications. Hailing from a small coastal town in New York, she credits Hurricane Gloria with fostering her interest in the weather. And with that, Marissa, I give you the floor.
Okay, thank you so much, Gideon. And yes, tropical storms and hurricanes are what got me into this business. So it was a thrill when I was asked if I could do this today. I'm happy to introduce Stephanie Zick, who studies tropical meteorology, tropical cyclones, precipitation, and model forecast verification. Her research focuses on using spatial methods to better understand tropical cyclone dynamics and structure, with a particular focus on hurricane landfall. Zick is an assistant professor in the Department of Geography at Virginia Tech, and we thank you so much for being here today with this breaking weather webinar. Take it away.
Yes, thanks for having me. I'm honored to be invited to do this. Definitely thinking of people in Hurricane Idalia's path. So we'll start out. Sorry, we're in the middle, but here we go. Sorry, let's start not in the middle. Here we go. It's just like my teaching where I make lots of mistakes. Okay, so yeah, so I'm an assistant professor at Virginia Tech. We're going to talk about Hurricane Idalia and the threat primarily to Florida, but definitely also to Georgia as we move forward. So here is satellite imagery from Tropical Tidbits. This is water vapor imagery. I chose this because it shows the upper level flow really well. That's going to help determine its future track. So we have Hurricane Franklin off here, sort of east of South Carolina, and I believe it was just completing an eye wall replacement cycle, so it's cleared out a huge eye. There's also another tropical depression out in the central Atlantic, and then we have Hurricane Idalia down here in the Gulf, and we'll talk more about that. I'm just going to point out a couple of features here. So there is a trough digging down sort of just south of Texas into the Gulf here. And then there's a pretty strong subtropical ridge. So we can sort of see this clockwise flow around that. And both of these features are going to be helping to steer Hurricane Idalia. Okay, and this is an update. We've got the 2 p.m. Eastern Daylight Time update. So 80 knots and 90 mile per hour for intensity, and pressure is down a little bit to 974 millibars. It has been slowly intensifying so far. We'll talk a little bit about why that is. This satellite imagery shows the visible satellite, and it is definitely starting to develop a better inner core, and we can see somewhat of that because of these convective bursts that are happening right in the eye wall. It has not cleared out an eye yet. There's sort of a little bit of dimpling through here that's suggesting that it might clear out an eye soon, but sometimes those can be false eyes, so you got to be careful. It does definitely look like an intensifying hurricane at this stage, similar to about that Category 1 status. We also see some rain bands that are already impacting South Florida. I want to talk just a little bit about the aircraft recon. We've had lots of missions into the storm. This is from a mission from yesterday, and they did their pattern around it, doing the center fix. I think this is like a figure 4 pattern. I'm not an expert on those aircraft missions, but so we can see though that we can see these wind barbs through here, and the strongest winds are on this southeast quadrant. So that's the down shear side. This is really a common feature in these storms that are sheared as they are, organizing. So the convection tends to be displaced down shear and down shear left. So the shear yesterday was out of the northwest, and we can really see with the cloud coverage that the most of the convections to the southeast of the storm, and the strongest winds are over there as well. What's cool is a lot of the data from these recon missions is getting assimilated into our models. This is just an example from the 12 UTC HWARF run from yesterday. So we've got tail Doppler radar that's getting into the models, and dropsons and these little green dots. And there's the G4 is the purple tail Doppler radar, and the blue one is the P3. So lots of information helping to hopefully improve the analysis and get a better forecast. This is also, I love this picture from Derek Herndon. He posted this to Twitter or X or whatever. So this is showing SAR winds. So this is synthetic aperture radar, and it really shows how asymmetric the storm was yesterday. So these stronger winds were all on the east and southeast side of the storm, consistent with that satellite, or consistent with the aircraft recon I was showing you. It's also sort of highlighting that as this storm moves up and is impacting Florida, like a lot of, it's still pretty asymmetric, and those strongest winds are on that east side still. So it's something to think about for the impacts in Florida. I want to talk a little bit about the inner core formation. As of yesterday, it still didn't have, it was very tilted. So these are tail Doppler radar wind data from yesterday. So they're from 14:35 UTC yesterday, so around, midday. So we see on the left-hand side, this is stuff from, I got this from Philly Papin. So on the left-hand side, we're just showing like this is the 1 kilometer winds, and the shading is indicating the strength of those winds. And we can infer where the 1 kilometer center is in this yellow. And as we moved up through the atmosphere on the far right, these were 10 kilometer observations, and that red circle is the 10 kilometer center. So we're seeing that there was this tilt towards the southeast for the vortex. So we're not having this like really rapid intensification so far. It's been rather slow so far. It's sort of just chugging along, organizing. We do anticipate this to more rapidly intensify now that as of today we are going to have a vortex that is now vertically aligned. But as of yesterday, it was still just intensifying rather slowly. So I have a little bit of information down here to this recent research by Falco Jute, and he was talking about sprint versus marathon rapid intensification. So far, it's been more of a marathon. It's going a little bit more slowly, and it's happening over many days. Okay, so this is more about that inner core formation from data from the tail Doppler radar wind data from today. So reflectivity is on the left in shading, and the winds are overlaid for 1 kilometer above sea level. And then on the right, we have the winds that are shaded with the wind barbs. Okay, and we're going to move up through the atmosphere. So this is 1 kilometer above the ground. We're going to move up to, oh, sorry, wrong way. This is 1 kilometer above ground, 3 kilometers, 6 kilometers. So we can go back. But basically you can see that it's now vertically aligned as of this morning. All right, and this is a really important process in the inner cores formation. Once we start to have a vertically aligned vortex, we can start to have more rapid intensification. And I'm going to just briefly talk about that. So this image on the left shows a schematic of what a hurricane structure is. And on the bottom down here, the little graphic here in yellow, red, and blue is showing where the wind speeds are, with lighter winds in yellow and the very strongest winds in the eye wall in red. And then overlaying it, we've got this kind of cross section through the hurricane. So we're getting its three-dimensional structure. And what we call the primary vortex is the spinning winds, those tangential winds. And then there's also a secondary circulation that brings moisture and converges mass towards the center of the storm and then up and out. So basically, once we get that vertically aligned vortex, we have the hurricane structure that's most efficient for further intensification. One of the ways I think about this is 37 gigahertz imagery. It's not from Idalia, but this is from IDA in 2021. And it's 37 gigahertz imagery, the color composite. And it's been shown through some past research that whenever we start to see this cyan ring on 37 gigahertz imagery, this often precedes rapid intensification. And this cyan color, this ring, is really indicating that there is rain completely encircling an eye. All right, so once we get that full enclosure of rain, or essentially, like that eye wall forming, at least in the low levels, that will often precede rapid intensification. So we're kind of at that stage, sort of like as of this morning, where we have this vertically aligned vortex. We don't have a 37, we don't have a good satellite pass, so I can't show you that, but there were really good radar animations from Cuba really showing that eye wall forming overnight. And just to drive this home, once we have this structure established, that can really, if we have a good environment from that point, we can have rapid intensification. And this structure is really, it's just more efficient once we have this structure set up. So now we're going to look at the environment, because once we have that vertically aligned vortex, it can really go through rapid intensification if there is a conducive environment. So I'm showing on the left the ocean heat content. This is from 6Z this morning. So that was its position for the 0 hour there at 6Z, and then a 12-hour and 24-hour forecast location. And what we're seeing is that the storm is moving over some pretty high ocean heat content. So this is a loop current in the Gulf of Mexico that it's moving over. So that's a lot of energy for this storm. The image on the right is showing, this is from Dr. Kim Wood, who's now at Arizona. So it's showing these Argo profiles, which are measurements of temperature down into the water, like below the water. And so we are seeing there's a deep pool of warm water that this storm has access to. And that's generally how these storms intensify, through evaporating that warm ocean water and releasing latent heat and moving through that Carnot heat cycle. So let's talk a little bit more about the environment. I'm going to look at, this is SHIPS data, and it's from Tomer Berg's website. I covered up the intensity forecast. I kind of made it dimmer because I don't want you to look at that. I want to focus on the environmental variables here. So the environmental variables are on the right-hand side. And we have from 0 hour on the left out to 168 hours. And these are some important environmental variables that can help to tell us whether the environment is conducive for intensification. The top one here is the forecast winds, which we won't focus on too much. Then the maximum potential intensity is based on the thermodynamic environment, so basically mostly the sea surface temperatures. So we're seeing that this storm still has a lot of room to intensify. Lower wind shear is more favorable for intensification, especially shear under 20 knots. And so we see for the next 24 hours, favorable shear. And then really warm sea surface temperatures up around 31 degrees C, and pretty good mid-level relative humidity. So on the top left here, this is the ship's rapid intensification product, and it gives probabilities of rapid intensification. And we see an over 50% chance here of rapid intensification of 25 knots over 24 hours. So let's look a little bit at the model forecast. These model forecasts are going to be from Tropical Tidbits. There's been a lot of consistency in the high resolution models in terms of like the intensity and the location of landfall. This is the 12 UTC run from today, August 29th, for 4 of our high resolution hurricane forecasting models. And they're forecast out to 24 hours. So valid at 12 UTC tomorrow, which is in the morning tomorrow. So we see quite a lot of consistency in terms of where this storm will be located with the L's at the center here. There's a little bit of variation in intensity that can kind of be inferred by like how cleared out the eye is. So the H-WRF and the HAFS-B have a slightly stronger storm, and the HAFS-A one is a little bit more asymmetric. But all of these are definitely possibilities, I think, still. So definitely could still see, I mean, these are all basically category 3 plus intensities here. All right, so let's look at the track forecast a little bit. So this is a loop from the ECMWF model, the 6 UTC run. We're going to loop through, I think, about 90 hours because I wanted to also address some questions that we might have about the track after Florida landfall. I'm showing the ECMWF, although I'll say that the HAFS-A forecast is similar. The GFS forecast is definitely a little bit different, but this is what I decided to go with. So we do see Franklin up here on the top right. And at the beginning of the loop here, we see Idalia. This is the 850 millibar relative vorticity and shading, so we can really track the storm really well. We also have 500 millibar geopotential heights on here in the contours, and then 200 millibar winds. So this can help us to understand how the storm is going to get steered, because that vorticity, it's on a first order, it gets steered by the large scale winds. Okay, so we can see the trough that was digging in over Texas. When we go back to the beginning of the loop, yeah, we can see this trough here, and we can see the ridging, this subtropical ridge, and you can also sort of figure out where that is based on these geopotential height lines. So those are the 2 features that are steering this storm, and it's generally on a northerly track. We can also see at the end of this loop here, so there's this jet streak up out in, okay, so let's watch again. And we see this jet streak. So that trough is helping to steer the storm and turn it off to the northeast, but it didn't pick up the storm. This is not a storm that's like going to go through extratropical transition and merge with the mid-latitude pattern. It doesn't get picked up, it gets left behind. So after that, there's not very strong steering, and we have a lot of uncertainty in the track forecast beyond about 4 to 5 days, especially. So here's the track forecast. This is from Tomer Bergs. He does a multi-model ensemble, which I like. So it's, you know, averaging the ensemble members for the ECMWF, the GEFS, UK Met, and CMC, so the Canadian model too. And so it's a good consensus forecast, which has sort of less jumping back and forth between model runs. And in general, the forecast has been pretty consistent. We see a little bit of difference back through time. So the official forecast is in black. And then the purple is the most recent model run, the most recent model consensus. And then as we go back through the lighter colors, those are older initializations, older runs. So there is a little bit of difference. It was having trouble, it didn't quite have the center found at the beginning because the storm was still so weak. So we had a little bit of adjustment towards the east as we had vortex alignment. But in general, the last few model cycles, it's pretty consistent in where we think it's going to track, at least over the next 48 hours or so. This is more broadly now looking at just the most recent cycle, the 12 UTC model runs, and some different models. So, the HMON, for instance, is this orange color. HWARP is this lighter blue. Okay, so we're seeing there's pretty good consensus on where the storm's going to track over the next 24 and even over the next 48 hours. But beyond that, we see model divergence because, how much is it going to get steered by that trough and how much is it going to get left behind? And the GFS in particular is really kind of having it circled back. But this is really too far out. I don't put too much definitely don't want to be looking at a 144-hour forecast at this stage. So focus on like the 3-day is good for now. Okay. And just one more thing on the track I want to illustrate. So this is a forecast from the 0Z model runs from today. So it's a little older, but I liked it because it shows the different uncertainty in both the cross-track and along track. So cross-track is where it might make landfall along the Florida coast. And then the along track is the speed. All right, so we're seeing that there is, there's still like a cloud of points here in this forecast, which I think I went out to 30 hours for the end point of all of these. And has been noted that there have not been a lot of landfalls in this location, this Big Bend region of Florida. So this is a graphic from Tomer Berg, and it's showing since 1851, all the storms that move within this rectangle. There's not that many, and there's actually a huge gap as you move around this Bend region of Florida. So they've been highlighting from NWS Tallahassee about how there have literally been no hurricane landfalls, no major hurricane landfalls in this region. And this is a region that is very vulnerable to storm surge. It's very flat. There's not a lot of elevation gain. So it's something to keep in mind. And the storm surge forecast is calling for 10 plus feet. And this is also a graphic from NWS Tallahassee. So how many major hurricanes have ever entered Appalachia Bay? And the answer is 0. So I think they're doing a really good job with messaging, and I hope that residents are getting this information. So there may be a question of how, this seems a little strange that there have not been any major hurricane landfalls in this region. So I was addressing a potential question. These are from the National Hurricane Center, and they're showing return periods for a hurricane force wind. So for instance, here near the Galveston area, or just south of Galveston, they see a hurricane every 19 years about. And then right here, every 11 years return period. And so the shorter numbers, those are that they see hurricanes more frequently, these red values. And I mean, it's basically a geography thing. So storms run into things that stick out. Peninsulas, North Carolina, right? And they're less likely to run into these coastlines that are concave. And so this is a major concave region, and it's just a little harder geographically to have a landfall there. I want to just briefly say something about these Big Bend landfalls. This is research from me This is out of my PhD, and it's published in the Annals of this is a geography journal. So I'm showing, these are shape changes in the storm structure. So the top figures are asymmetry. So we're showing, is the storm becoming more symmetric or less symmetric? And then dispersion is a measure of how close the precipitation is to the center of the storm versus is it dispersed away from the center of the storm. So we're looking at shape changes. And something I found in this study is that storms that take a track, like we're expecting to see with Hurricane Idalia, they tend to be becoming more symmetric. And this is a little different from storms that are making a track more maybe towards the Western Gulf. That's another common track. And I'll just say there's 3 panels here because they're just different averaging boxes. This is like a geography problem. We want to make sure that if we modify the region we're averaging over, we get the same answer. So I did the averaging over different sized averaging boxes, and it got basically the same solution. So it's fairly common for storms making landfall in this Big Bend region to be becoming more symmetric. They are also becoming more dispersed, and I believe that's because they're encountering shear, essentially, or they're interacting with a jet stream. That can be something that hinders intensification, but if it's in the right jet quadrant, it can also aid with difluence, which can lead to more intensification, which is something we probably saw in Ian last year. This is the NHC forecast. And so we've got, we're finishing up soon. So we've got our major hurricane at landfall. The main thing I want to highlight here is that there are tropical storm watches and warnings on the East Coast. All right, so there's going to be heavy surf on both coasts. And the key messages from the National Hurricane Center, they're really talking about storm surge inundation. I'll just highlight that one on the top. So this line of purple along, it's between, I don't know, I can't read these, but it's like sort of the Cedar Key region back towards Apalachicola. So that region is expecting the highest storm surge, and they're forecasting 10 to 15 feet. And there are multiple threats with a hurricane. It's not just the category based on the wind speed. So there's wind, storm surge, rain, and also tornadoes. All right, and I believe that's it. So we can open it up to questions.
Okay, Stephanie, a few questions came in while you were presenting. The first one is from Gene Norman, and he wanted to let you know this was great information. But at what point does this kind of storm's angular momentum overcome any shear?
Are we talking about?
This was sent when you were showing the how the storm had been sheared earlier. There was the shear coming from the northwest, and it hadn't started intensifying yet.
Yeah. So if I may be understanding the question correctly, so this is during sort of the early stages of development. So overcoming shear, honestly, this is a huge research area. Shear, we do know that shear over about 20 knots can be very detrimental to storms. Storms that have already developed and they're like category 3+ already, they have a lot of inertial stability. So they already have very strong winds, and it's harder to negatively impact them. Their stronger storms are a little bit more resilient to shear, essentially. Weaker storms are not as resilient. They don't have, maybe as much angular momentum, as much inertial stability. And so they can be a little bit more vulnerable. In this case, it was in a very, very favorable thermodynamic environment, and it was able to fire enough convection to eventually overcome that shear.
Okay, and if we didn't answer what you were asking, Jean, just put another question in there and we'll let you know. The next question comes from James Duncan, and this is with regards to the recon data. And the question is, does the flight data, radar data go into the CAM models, meaning the NAM, which is showing a more westerly track in the Carolinas versus what the GFS and the European are showing?
So I don't have a graphic like this for other models. I got this from Jason Sippel, and I don't know that it's publicly posted anywhere. But all of these data can get assimilated into the models. They go to like a larger, I guess, repository maybe is what you might call it, and they can get ingested. Each model has its own data assimilation system. So it's hard to say whether they get rejected or they get incorporated without having this sort of information for the NAM. But yes, I mean, ideally they are getting assimilated into all the models. And I haven't looked at the NAM forecast very closely. Honestly, it doesn't tend to be a very good forecast for hurricane forecasting, so I didn't even look at it.
Okay, well, I'm going to move to the next question from Rick Halterman. And Rick says, it seems that more often storms are slowing in forward motion at landfall. Is this impression correct? If it is correct, what is causing the reduction in forward motion?
Yes. So there is sort of this sort of anecdotal, I guess, that we seem to have a lot of storms slowing down. And research does show that we are seeing more storms slowing down, kind of similar to a Harvey situation or a Florence situation. There are others that probably could answer this a little bit better. The way that I understand it is, in general, the storm steering is weaker. We have less of a temperature gradient between the tropics and the poles due to climate change, and so we have less sort of like our jet stream is getting a little bit slowed down and potentially a little wavier. Like I said, this isn't my research area per se, but I think that's the reasoning. If there's anybody else on the call that has a little bit more experience with this, definitely feel free to add that in.
Okay, the next one is from Catherine Flaumer. And we've heard of record ocean temps around Florida this summer. Is the water over which Idalia will be moving anonymously warm right now?
Yes. I don't have any graphics showing how anomalously warm it is. Kim Wood did actually post something, I think yesterday or this morning on Twitter about that. It has been anomalously warm. I believe it's been the warmest on record in the Gulf of Mexico and a couple other regions, depending on like where you create your averaging region. So yes, it's anomalously warm. Interestingly, the Gulf has cooled down a little bit in the last couple of days, but it's still warmer than average, a lot warmer than average. And with moving over this loop current, that's always like just a favored region where you have really deep, warm water.
Okay, well, thank you for that. Now we have one from Vivek Shenoy. Are there any regional thermodynamic and dynamic reasons having to do with the bathymetry why storm tracking in the Western Gulf of Mexico display a tendency to become less symmetric?
Oh, okay. Are we going back to my research? Or can you repeat that, Marissa?
Sure, it was a long question. Are there any regional thermodynamic and dynamic reasons having to do, and I'm probably mispronouncing this word, with bathymetry why storm tracking in the Western Gulf of Mexico display a tendency to become less symmetric?
Okay, yeah, so I think this is going back to my research. This is something I want to return to. It was based on tropical cyclones from 2004 to 2012. So it's not up to date for sure. And since then, we've had a lot of rapid intensifications close to land. I'd really love to go back and look at this to see if there have been any changes, in like the more recent decade. And then also look at environmental variables. what might lead to a more symmetric storm versus a less symmetric storm. And, shear is one thing that I have looked into in the past, but there's also other factors like sea surface temperatures, not just shear, but like the position of the trough with respect to the storm. So more of a synoptic analysis. Yeah, and I do think it's possible we would get a slightly different answer if we did this, if we expanded this through present day, or if we just looked at a slightly different averaging period, say from 2012 to 2023 or something.
Okay, well, the next question comes from Richard Redding, who says, thank you for your presentation. Richard asks, hurricanes Ian, Irma, and Charlie made an early eastward turn as opposed to the forecasted north path. What causes this to happen?
Yeah, this is a great question. And I think it's just really hard to forecast these very slight. So one of the, I actually have a graphic here that might be helpful. Sorry. Very slight shifts in the synoptic environment can lead to just like these little differences in track, and those differences in track grow with time. So I'm sorry, very sensitive. So, with this particular storm, and similarly with Ian, there's this subtropical ridge, which is a common feature in our subtropics, up to the east, kind of over our greater Antilles down here. And then we've got a trough here. And how these two things interact with the storm are going to steer. So like the trough, right, is digging, and then we've got, it's steering the storm off to the northeast. But then there's anticyclonic flow, counter or clockwise flow around the high that's also steering it that direction. So very slight differences between the model forecast and reality can lead to these little differences in track that grow with time. So for example, this is the ECMWF forecast for the last, I think, 3 cycles. So we have the 60 is the last one that shows up, but then there's also a 0Z and an 18Z. And there's just these very slight differences in the strength of this subtropical ridge. And you can, if you just look at this 588 line here that's bisecting Florida, you can see that it shifts to the left, okay, with time. So the ridge is a little bit stronger in these more recent model runs. And the storm has actually, the forecast, these models have shifted it a little bit to the west, ever so slightly, right? So that hopefully answers your question. I think this is also magnified because we have a storm moving northward parallel to the coastline. And so, little changes in these features can make big differences in the landfall location when you have that scenario.
Okay, well, we have a follow-up from someone else here regarding that question. Would cyclone momentum within the storm itself help turn it slightly east as the storm gets stronger?
So there are 2 main, when I think about how a storm motion, there are 2 main influences on storm motion, and the first is the steering. Right, so this is the large scale environment that's steering the storm. It's not exactly like a cork that's bobbing in the ocean and getting steered. It is also a vortex that interacts and does its own things. But on a first order, just that large scale steering will give you an idea of how it's going to track. Additionally, it is a vortex that it's advecting its vorticity around it. And so there's these asymmetries associated with the vortex because it's advecting higher vorticity air this way and then lower vorticity air this way if we're thinking about planetary vorticity. So you get these asymmetries within the vortex that also help to steal the storm. And that's actually why storms, so that if they were in like a straight easterly flow, they don't just go easterly. They actually move a little bit poleward. All right. And that's due to those that vorticity advection and the asymmetries that develop. It's called the beta effect. Those are two main factors. I mean, additionally, there's also these asymmetries that can help to steer this, not help to steer, but there's these asymmetries within the storm that can lead to slight differences in track. I've only seen research into this like on a research level. I don't see people in operations looking at potential vorticity and how that's going to affect the track. But they are important influences potentially. It's just I don't know that we are able to diagnose them in real time, and it's more of a research realm, I would say.
Okay, if anybody else has any other questions, feel free to pop them in the Q&A field here. I actually have a question. The track of this storm, once it goes overland and back out to the Atlantic, it looks like, and I may be wrong here, but it does look like it might be located where Franklin currently is. Will Franklin have any influence on that, you know, in the coming days when, you know, the end of this week when Idalia might be out there in the Atlantic near where Franklin is now? Because the reason I'm asking is these storms tend to, there's upwelling going on. So Franklin may be the surface temperature might be cooling off where Franklin is currently located. And will that have any bearing on Idalia? And also will just the steering winds because of Franklin have any bearing on Idalia?
These are good questions. So there should be definitely upwelling underneath Franklin. So there's going to be some cooler waters out here that it's moving over, and that should limit the intensification. Sorry about that again. I was looking at this a little bit. They're getting close enough at places where I was wondering if the vortexes would interact. So they can start to rotate around one another, the Fujiwara effect. It's not obvious to me that we have that here yet, and maybe are not quite close enough. So I think mainly they're both getting steered by this trough, and honestly, it doesn't look like either one's really getting picked up by the trough entirely. I think Franklin, I haven't looked at Franklin as closely, but it didn't look like Franklin was getting picked up in this particular model run. It looks like it gets left behind too.
If anyone else has any questions, feel free to put them in the Q&A. We're talking about Hurricane Idalia with Dr. Stephanie Zick, and a big storm that could have an impact on a huge area, not just where it's going to make landfall. So that, I think, is one of the important messages. And okay, we have a question here now from Jen Bewley. How good are the models at predicting rapid intensification? Do you think there is a chance that Hurricane Idalia will become a Category 4 or 5, similar to Hurricane Michael?
Yes. So this is something we've been devoting a lot of resources to. Actually, I'll just go to the last slide I had in here. I had an extra slide looking at the intensity forecast. Oops. Sorry about that. Okay. So we now have 4 high-resolution hurricane models, and that's kind of amazing. I think each WRF is going to get retired soon, so this isn't like we're not going to have 4 forever. But we have 2 versions of the HAFS model, and they have the same model core, so sort of the same dynamical equations, but they have different model physics. So it's kind of like a mini ensemble of the HAFS, which is kind of cool. And we have like a kind of a 4-member ensemble of high resolution forecast models. These hurricane forecasting models have been developed. There's been a lot of resources towards trying to capture the internal processes that are associated with rapid intensification. So things like vortex alignment. And so not only they're higher resolution, but they're more advanced in terms of the physics. They also have what they call scale-aware convection results. So in the old days, you either had your convective scheme on or off. And if you were running a low resolution model, you wanted to turn on your convective scheme. And if you ran a high resolution model, you wanted to turn it off, because then the model would generate its own convection. Now we have this scale aware convection, so it can kind of have this gray area I think it's great. So we've got a lot of advancements. And I think these models are getting a lot better at predicting rapid intensification. And I know the stats from the last few years really show this. Our intensity forecasts have been improving, and that had been a big foil for decades. So yes, I think that they are getting better at this rapid intensification. And we can see that many of these models are forecasting rapid intensification. So rapid intensification, that wasn't defined, but it's essentially about 24 knots in 24 hours. So this is, the forecast based on these various models for the intensity. And so a lot of these models are forecasting from about 70 knots up to 110, 120 knots. It doesn't mean that these are going to be perfect, but when you see a lot of consistency, like 4 different models all predicting rapid intensification, it does give more confidence, alongside the fact that we see a favorable environment in which these storms do tend to rapidly intensify. So when all these factors come together, I feel like our National Hurricane Center forecasters have gotten so bold in predicting rapid intensification, and they're getting just really skillful at it too.
Okay, we have another question here from Tan Dow. Tan would like to know what causes hurricanes to wobble a bit on their track, independent from the steering influence.
Yeah, that's a good question. So there's these little wobbles. Sometimes I wish I had some more graphics to go along with this, but yeah, these storms, they call it a trochoidal motion. So if you follow the center of the storm perfectly, they make these like circles, which they look like wobbles, but the center of the storm's not following a track like this. It's doing these little like circles. And that's due to asymmetries in the eye wall in particular. I believe that's one of the main reasons. Actually, I have to go back and look into that, go back and do my lit review. But yeah, so they do these little wobbles. And that can be something like a 10 to 20 mile difference in the landfall location when you are you on this side of the wobble or that side of the wobble, right?
Okay, we only have a few more minutes, so if you have any questions for Dr. Zick, please put it in the Q&A. Oh, no questions right now. But big storm heading towards Florida right now. A lot of inland areas can be impacted by the rainfall. You just had that graphic there, Stephanie, with the possible impacts of the storm. And I know the National Hurricane Center and the National Weather Service has been working really hard the past few years to talk about impacts on populations. So if you'd like to just talk about that once again, that'd be great.
Sure. Yeah, there's been a lot of focus in the public and maybe in the media on the category of the storm. And there's been a real effort to message more around the impacts. So I think one of the things that came out of that is the key messages, focusing on the key messages rather than the category of the storm. And then this was another graphic that they put together that I think can help to highlight. So we move away from just a cone of uncertainty and we think more about the impacts, these individual impacts sort of discreetly. And they do overlap, but there's still, so there's more than wind, right? The Saffir-Simpson hurricane scale is a wind scale. So that is based purely on wind, and it's a sustained wind in like one location. So it doesn't tell us anything about the size of the storm. It doesn't tell us about some of the most deadly aspects of the storm, which have historically been the water. So the storm surge and the rain collectively. And it depends on the storm. Sometimes it's more coastal flooding and sometimes it's more inland flooding. But that's what we want to be doing. We want to be focusing more on these impacts. So we do have the wind graphic, which is now like a two-dimensional map showing what winds we might expect. And then the storm surge that we might expect along the coastline. And rain can be big rainmakers. These storms, they bring with them a lot of moisture. And this storm is going to be moving. It's not expected to stall, not at least in the first few days. It might stall a little bit out over the ocean later, but it's expected to be moving. So that will help with the rainfall totals. But still, it's a big tropical storm. And I think they're forecasting like 10 plus inches localized. I haven't looked at the most recent rainfall forecast. They might have upped that a little bit. And then the last thread here is tornadoes. So particularly in the outer rain bands and on the right side of the landfall location, we have good environment for supercells. So tornadoes can get spun up even pretty far away from that storm center, right? So these threats extend way away from the eye. And a tornado threats are a really good example of that because those are often in the outer rain bands.
So last call for any questions here. We'll be wrapping up here momentarily.